Well, let's go through this worksheet that we went over in class. So the first question, the B effective for one proton differs from the B effective of the other, which makes sense because we see different gaps between proton 1 and proton 2. Now the question is, what is it asking? Which proton requires a higher, first question, which proton is shielded to a greater extent? That would be proton 1 is shielded because the gap there is smaller than that gap. And I don't know why that does that. Darn it. And so the proton 1 has more electrons around it, or electron density is probably a better way of saying it, and hence it's going to be shielded from the external magnetic field. So it's not going to feel as much of the external magnetic field, and so that gap between the alpha and beta states will be smaller. If asked another way, which proton is deshielded the most, you would say proton 2 because it has a much larger gap. Now, which proton requires a higher frequency radio wave? Well, that would be proton 2 because the energy gap is larger, so it's going to require a higher energy photon. So question 2, look at the chemical shifts for protons attached to the fluorine. So what you're going to see is the electronegativities of the halogens. Okay, let's see here, back to there. The electronegativities is going to get larger. So it's something that you recall seeing from Gen Chem. As the electronegativities get larger, so that's the largest, that's the smallest in this example, you're going to see a greater chemical shift for that guy. So that goes with that. You can see, so what you're going to see that the trends of the electronegativity for the halogens is going to follow the chemical shifts of the protons that are connected to those same halogens. Will the chemical shift of the proton be greater for this one, or that one? Well, we see the CH2, Cl2 has 2 chlorines that are going to inductively deshield those 2 protons. In contrast, we have 1 proton that's now going to be electron density is going to be pulled away from it due to the inductive effects of 3 chlorines. So 3 chlorines are going to have a stronger inductive effect than 2. So between those 2 molecules there, you would expect this proton right here to have a larger chemical shift or a larger parts per million and would be further downfilled than those 2 equivalent protons right there. Question 4, ethylbenzene is used primarily in the production of styrene, the precursor to the polymer polystyrene. It is also, component of fluids that can be injected underground as part of a process to recover natural gas. Rank the indicated hydrogens with the largest to smallest chemical shift. If we zoom in here a little bit, we see a hydrogen directly attached to a benzene ring, one on the benzylic position, and then a hydrogen that's getting further and further away from the benzene ring. Based off of the molecular anisotropy lecture, we would expect that proton to be the furthest downfilled. And then as the protons get further and further away from that benzene ring, it just tapers off. So we would expect this one right here to be the furthest downfield, then that one, and then that one. Those are the relative chemical shifts. If you want to get numbers associated with those, then go back to the PowerPoint slide or the video where I showed you those chemical shifts. Okay. Rank the protons from the largest chemical shift to the smallest. Well, this one, when you go and look at your NMR tables for chemical shifts of protons, you'll notice that we have an aldehyde hydrogen there, and that's going to be the proton furthest downfield. That has a ppm of like 9 to 10. So we would have D with the greatest chemical shift. And then we have protons on carbon G that's directly attached to that chlorine. And so we would expect G to be the next one. Now it gets a little tricky now when we're comparing E, F, and H. But the way I like to look at it, comparing this carbonyl to the chlorine, and then looking at the hydrogens that were attached to it. So we have this hydrogen right here that's coming off, and that's proton G. Which entity, the chlorine or the carbonyl, which had a greater effect on the chemical shift of the proton? And clearly you would say the carbonyl, because that carbonyl is responsible for the downfield shift of the aldehyde proton, around 9 to 10. That's pretty big. And that's whenever you have a chemical shift around 9 or 10, almost always it's just screaming, hey, you have an aldehyde. Whereas proton G wasn't that far downfield with respect to D. So we know that the carbonyl has a stronger effect, and that is due to the molecular anisotropy. So, but we've also learned that molecular anisotropy also affects the protons that are getting really close to it. So if the carbonyl has a stronger effect than the chlorine, then you would expect E to be further downfield than, let's say, F or H, because it's really close to that carbonyl. So we would, based off of that logic, we would see E would be the next. Now it's between F and H. Okay. Now, F and H have this in common in the fact that H is one carbon away from this carbon, and F is also one carbon away from this carbon. So the distance there, the same. But what does F have that H doesn't? You can clearly see that F is closer to the carbonyl. Hence, we would expect F to be further downfield than H due to its proximity to the carbonyl. Okay. So how many signals would we expect for this one? Now this is where we have to be very, very careful in the fact that you cannot just draw all these protons here, here, and here, and there, just with lines. You have to show the geometry of the molecule. So we have some protons here. You know, I'm going to have to actually draw this a whole lot bigger. Just to help us out here. Okay, so we have a chlorine right here. And when you take a closer look at that, you can see that that is a stereocenter. So you have to pick this. It's not telling you what it is. So you just have to guess. We'll just put it as a wedge. Now when you take a look at that, what is the relationship between these protons between themselves? And then we have to figure out what's the relationship between these as well. Now you can do a plane of symmetry argument here if you'd like. And since you can't see me, that's going to be a little difficult to do. So what we're going to be forced to do in this example would be a replacement test. So the first question that I want to ask is, what is the relationship between these two protons right there? And the way that you have to do that, like every other replacement test, you have to make two molecules and replace one with an X, and then draw another molecule like that. Now we have to ask ourselves, what is the relationship between this proton or that molecule and that molecule? If I call this one A and this one B, if I take B as is, can I pick it up and just drop it on top of A and everything superimposes? And the answer is most of the atoms will superimpose except for the X's. In A, you see an X with a dash, and in B, you have an X with a wedge. So that won't superimpose. Now, can you find that B and A are mirror images to one another? And in order to try to do that, you would have to take B or A, doesn't matter, but I'm going to take B, and I'm going to flip it 180 degrees to make it look like this. Because what I'm trying to attempt to do is to get a mirror image. And so if I take B and flip it 180 degrees, then now the chlorine atom right here is going to be a dash. And then my wedge and dash right there is going to flip. So that will be an X, and that will be the proton. And so this molecule right here is still B, but I'm going to call it B prime because I took the original B and flipped it 180 degrees across the horizontal or the vertical axis to give us B prime. And now you can see B prime and A are not mirror images and not superimposable. Hence, by definition, that will make them diastereotopic. So if those are diastereotopic, then they are not equivalent, hence giving two separate signals. So we say signal A and signal B. So those two protons right there, two different signals. You'll do that same replacement test with the protons above here, and you will find also that those are diastereotopic. And the proton for the aldehydes is just one proton. That will give a signal. And then we have our methyls right here, CH3. And those methyls are going to give a signal all by themselves. And so then there's one more that most people, a lot of people, not most, we'll say a few people, there we go, will forget that there's a hydrogen right there. And so that molecule right there will have 7 signals. All right. Now you can also use the plane of symmetry argument for this molecule right here. Okay. And I can verbalize it, and hopefully you can translate that visually here. You would take that molecule as is and rotate it 90 degrees out of the plane and take your eyeball and look straight down the molecule, and you will see that there's no plane of symmetry. And if that's difficult for you to see, then you have to make a model or come to office hours and I can show you. Okay, so we worked on this problem in class. And recall that all we did was take a measuring tape or a ruler and just measured from that plateau to that plateau, and that distance right there was 0.5 millimeters, and that distance from there to there was 1 millimeter, and from there to there was 1.5. And so you can't have a half a proton, so we're going to have to multiply those ratios. So 0.5 to 1 to 1.5. If you multiply that whole ratio by 2, then we'll have 1 to 2 to 3. And if you add those up, that can equal 6 protons. Okay. So what we can say now is that this corresponds to that signal, that to that signal, and that to that signal. So what we can say is that this signal right here is a species that has 3 hydrogens. Or that signal corresponds to 2 hydrogens. And then that signal right there corresponds to 1 hydrogen. But remember, those are all just ratios. So we could also have a situation where we take that same ratio but multiply it by, let's say, 4. Okay? What's that going to do to these numbers here? If I do it by 2, 0.5 times 2 equals 2. 1 times 4 is 4. And then 1.5 times 4 would be what? 8? Or I'm off on that. That would be 6. So with that ratio, you can see that is no longer 12 or 6 protons, that would be 12. So in that situation, that same signal could actually mean that there's 6 protons, that one would be 4 protons, and that would be 2 protons. Okay. So this part right here, roughly how many times more protons contribute to the former to the latter? So what that simply is asking is how many protons are here and how many protons are there. Okay, roughly how many times more? Well, if I'm using these new numbers where that's 2 and that's 6 protons, how many more protons, how many times more are there for that guy? Well, 2 times what equals 6? 2 times 3. So this signal right here, okay, the integration right there, is going to give you 3 times as many protons as that signal. So that's what it's saying, or what it means. So this one, how many protons are coupled to the one that gives rise to each of the signals below? Well, we have to understand that if we have a doublet, that means you have a proton or group of protons adjacent to a carbon that has only 1 proton. So for example, if you had a molecule that looks like this. Okay, right there. And now we have 2 protons right there, and those are going to be equivalent. Okay. Now, those A protons, when we look at the adjacent carbons, we have nothing there, so we can ignore that one. But if we go to that adjacent carbon, what do we have there that's not shown? There's 1 hydrogen. So HA is attached to this carbon. We look at the adjacent and ask how many protons are there. And since there's only 1 proton, the n+1 rule states that there's only one proton. So 1 plus 1 equals 2, giving us a doublet. So these protons right here are HA, those guys right there. HA is split into a doublet because the adjacent proton, this guy, there's only one of them. 1 plus 1 is 2. Now, this one right there, what do we have? We have a pentet. It has 5 signals right there. So that means its adjacent carbon has 4 protons. Now, how's that possible? Because the carbon can't, that's not possible in a molecule that it would be bonded to 2 carbons and then 4 protons. So what that's saying is, I think it's best just to do an example and show you what that means. But what we can say is, since there's 5 signals right there, or that signal has been split into a pentet, that means that there's 4 equivalent hydrogens that are splitting the proton of interest. So for example, if I have this molecule like that, how many signals are there? Well, we will first figure out that these 2 protons right here are equivalent to one another. And then we have these protons that are equivalent, and those are equivalent to one another. Okay, so now we are taking a look at the splitting pattern for HA. So we have 1 signal for those 2 protons, HA, and when we look at the adjacent carbons, those hydrogens are attached to that carbon. So where are the adjacent carbons? Right there and there. And since those 2 adjacent carbons are equivalent, you just add up all the protons. So there's 1, 2, 3, 4. There's 4 protons. So the n+1 rule states that 4 plus 1 equals 5, giving us a pentet. And that's what we would expect. Now for C, that is a singlet. Now what can make a singlet? Something that looks like this. So I'm interested in these protons right here on the methyl. So those methyl protons are attached to this carbon right here that I'm highlighting in red. So where's the adjacent carbon? It's right there, and there's only one of them. So the n+1 rule states, hey, on the adjacent carbon there's 0 hydrogens. Plus 1 equals 1, which means it's a singlet. And so those methyls right there are going to split into a singlet, or not even split actually. Give us a singlet, and then if we add another layer to it, if we looked at the integration, that would also have to integrate for a ratio of 3 because we have a methyl group. Okay, taking a look at these. So an unknown compound produces a proton NMR spectrum that has just 2 signals, each of which is a singlet. Which, hang on one second. So with this problem, we need to figure out how many signals there are and then the split patterns. So for molecule 1, doing some symmetry arguments, you can figure out rather quickly that these protons right here are going to be equivalent to one another. And then these protons right here are going to be equivalent to one another and to the other side, because there's a plane of symmetry. And then these protons right here are going to be equivalent to one another. And the same with that. Now, if you don't understand why they're equivalent, then there's the plane of symmetry, axis of rotation, and you could do the replacement test. So like all those things, if this is difficult for you, you need a little bit more hands-on help. So please come to office hours or reach out to some tutors. So HA, okay, is going to be split by HB. But because this molecule right here has some symmetry right here, we only have to worry about the 1/2. So all we have to do is worry about those protons there. They get split by what? HB. And so if we do our n+1 rule, HA is attached to that carbon. So what's adjacent? Right there. How many hydrogens are attached to that adjacent carbon? There's 2 HBs. So 2 + 1 = 3. So HA is going to be split into a triplet. Now if we look at HB, what do we see here? HB, let's use a different color here, is attached to that green carbon. What's the adjacent carbon? Right there. And that's the same problem right here. Okay, so that would equal 3, which would equal a triplet. Now, why does HB right here not get split by that HB? Because they're equivalent. You only get split by protons that are not equivalent to one another. So if we take a look at the molecule 2, we have a chlorine in the plane, double bonded O. Now we have our wedge and our dash, and then our methyl. So we know the methyl is going to give its own signal, and those two are going to be equivalent to one another. Oh, not A, sorry. Those would have to be B's. There we go. So A is attached to this carbon. What's the adjacent carbon? Right there. How many equivalent hydrogens are on that adjacent carbon? There's 2. So that would split that into a triplet. So A equals a triplet. HB is attached to that carbon. What's the adjacent carbon? That one, and there's nothing there. So we just ignored that one. But then there's this adjacent carbon right there, and how many hydrogens are attached to that? 3. So 3 + 1 = 4, which is a quartet. So HB gets split by HA into a quartet. So we can annotate this so far. So those protons here are triplets. And, oh, they're all triplets on that guy. And, well, we'll keep it the way I've done it so far. And if we do this other molecule, molecule 3, what I notice here is if I take this bond right here, that I'm highlighting in green, and then just draw it like this, just horizontal, look at what I can do here. Okay, you see something there? So let's connect that. So let's make sure we have the carbon count correct. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. Why did I do that? Why did I rotate around that bond right there? Because now what do I have? I have a plane of symmetry. So what that does for me is that it says, hey, there's a plane of symmetry that says that proton or carbon, the methyl on 1 and 6 are going to be equivalent. But are they enantiotopic or homotopic? Well, if we look at this plane as also a axis of rotation and rotated 180 degrees, you won't know the difference before and after the rotation. So methyl groups 1 and 6 are actually homotopic. And so we have one signal for that. So we could label that A and A, both giving a signal. And then 3 and carbon 3 and 4 both have what? A wedged and a dashed hydrogen. A wedged and a dashed hydrogen. What's the relationship between the two wedged hydrogens? Those are going to be homotopic to one another. And then what's the relationship between the two dashed hydrogens? Those are going to be equivalent to one another. But then what's the relationship between those two? And those two are going to also be homotopic to one another. So what we have is only two signals. We have signal A and we have signal B. And signal A, since there's a plane of symmetry, we only need to look at one of them. So let's look at this carbon in green. What's the adjacent carbon? That one. So 0 plus 1 equals 1. So A is going to be a singlet. Now, let's see here. Now, HB, okay, there's the proton. What's the adjacent carbon? It's not this one. Why? Because those are equivalent. The adjacent is right there. And how many hydrogens are on that carbon? 0. So 0 plus 1 equals 1, which equals a singlet. Okay. So we have a molecule 3 has two signals, and all of them are singlets. Now let's finish up molecule 4. So if we have ourselves a 6-membered ring, double bond, so now we have a wedge and a dash, double bond, wedge and a dash, wedge and a dash there. Okay, so what is going on here? So those two are going to be equivalent to one another. Those are going to be equivalent to, there's only one signal here. So if you did a replacement test, you would see that you could flip and rotate the two molecules and they will be superimposable. So let's take a look and do one example real quick of that with the replacement test. Let's replace that with an X there. So let's compare that one to that one. What's their relationship? And I've already said that they're equivalent, but let's show it with the replacement test. There we go. So we will call that molecule A and that molecule B. Now look at what we can do here. Okay. What if I took B and just rotated, just like on the face of a clock, rotated that way? I'm going to rotate it until I get it to look like this. So if that's carbon 1, carbon 2, carbon 3, carbon 4, like that. Watch what I'm going to do. I'm going to rotate until I get carbon 1 right there. And carbon 1, since I've just rotated like on the face of a clock, I'm still going to have my wedged X like that. And carbon 2 is going to have my double bond there, double bond there. Let's see here. So 1, 2. Okay. Now we have B prime. Just rotated it. Now can you see how we can pick up B prime and just plop it and superimpose it right on top of A? So that makes them identical, which is homotopic. So we only have one signal for molecule A. And what would the splitting pattern be for A? Well, since they're all equivalent, we just have to look at this one. There's the carbon that's attached to the two protons. What's the adjacent carbons? Right there and there. And they both have 0 hydrogens. So 0 plus 1 equals 1, which is a singlet. So H4 also has just singlets, but there's only going to be one signal. So what did the problem ask? Which has 2 signals, each of which is a singlet? That would be molecule 3. Okay. Let's see the last problem here. Okay, determine the number of signals that would be generated in the proton NMR for the following compounds. Predict the splitting patterns for each signal. Okay, so if we take a look at molecule A, I would first want to redraw like that, and I notice that we have a stereocenter. And then we have our dashed hydrogen like that. Now, is there a way to find some symmetry? And so what I'm going to do here is I'm going to rotate around this double bond right there. Okay. And so what I'm going to do here is I'm going to rotate it in such a way as to get the chlorine right there. Wait, so that's not going to work. How is it? I've just changed my mind. Yeah, never mind. Let's scratch that whole idea of what I was trying to talk about, okay? So how many signals do we have? Well, we have this methyl right here. We'll call that signal A. And that methyl over there is different than this methyl over here. And one way to prove that to you is with the replacement test by just showing that I'm going to replace that whole methyl group with an X and that methyl group with an X. And so what's the relationship between those two? Well, there's different connectivity, same molecular formula. So those are constitutional isomers. And so that would mean that they have to be different signals. So that methyl group right there is a second signal, and then this lone proton by itself is a signal. Okay, so we found out how many signals. There would be 3 for that molecule, but now let's figure out the splitting pattern. So we'll look at HA. HA is attached to this carbon right here. Where's the adjacent carbon? Right there. How many hydrogens are on that adjacent? 0. 0 plus 1 equals 1, which gives us a singlet. Now, what about HC? HC is attached to that carbon. And so the adjacent one would be right there, so there's nothing there. So we could say it's a singlet if you wanted to. Or we go to this adjacent carbon right there. Whoop, that's not. That's my adjacent carbon right here. How many hydrogens are on that? There's 3. So HC is going to be split into 3 plus 1 equals 4, which is a quartet. And then HB is attached to that carbon. What's the adjacent one? Right there. There's only 1 hydrogen attached to that adjacent carbon. So 1 plus 1 equals 2 equals a doublet. Now, some may be wondering, hey, when I'm looking at HC, that's adjacent and that's a singlet, or there's no protons there. Why do I say sometimes to ignore it? But why in HA, right here, why do I count it? Well, it has to do with the fact that HC has 2 non-equivalent adjacent carbons. And so what happens is, let's do a splitting tree. Okay, so HA has a signal. And that's represented by that line. That's the NMR signal. Now, its adjacent carbon has no hydrogen, so it's not going to get split. It's just going to stay as a singlet, or one signal. But when we take a look at HB, HB would give us a signal, but that signal is going to get split into a doublet because HC is going to take that signal and split it into a doublet. So now we have two peaks. Like when we see a doublet in the NMR, that's a poorly drawn doublet. Should be a little bit sharper, but either way, those peaks right there correspond to the splitting tree. Now, HC on the other, when we take a look at HC, okay, it has 2 signals that we have 2 adjacent carbons to take into account. If I'm looking here at my carbon, what's adjacent? Right there. So that's going to take the signal and just keep it as a singlet. It's not going to split it. But then when I go to HB over here, we see that there's 4 protons, so that's going to split it into a quartet. And so there's the 4 signals. Or it took the signal of HC and split it into the 4. So technically when you're looking at HC right here, you can look at the adjacent and say, hey, that's going to be a singlet. But then there's a second one, and that's going to be a quartet. Singlets don't split anything. Okay? So annotate that on your molecule and make sure you say how many signals there are and their splitting patterns. Okay? So let's go to the next one. 1, 2, 3, 4. So is this the molecule of interest? I'm doing a recording. Okay, thank you. Okay, so there's, I believe that's the molecule. So now we have to make sure we understand the stereochemistry, and whatnot. So we're going to redraw that molecule to help us understand some stereochemistry here. Like that. Okay. And then we have some hydrogens here. Like so. Okay. Now sometimes it's easier to like rotate around single bonds and change it a little bit so you can see the symmetry argument. So what I'm going to do, okay, is I'm going to take these pieces right here, and just like a steering wheel in your car, I'm just going to turn it in such a way as to put the hydrogens there and the 2 chlorines right there. And then I'll do the same thing on the other side. I will put the hydrogen here and then the 2 chlorines right there. 1, 2, 3, 4, 1, 2, 3, making sure I have the proper carbon count there. Okay. And now we can redraw it again. And I'm just doing this iteratively so you can see my thought process here. Now I could redraw it like this. So that's staying the same. But now I can take this part right here and then, let's see here. No, now that I'm thinking about it, maybe we're fine. No, we're fine. Okay, so now we have our hydrogens here, here, like that. Okay, so what's the relationship between these two? Hopefully you see that there's a plane of symmetry cutting right through, making those guys equivalent. So we would call those HA and HA. Now what's the relationship between those two? Well, that would be the same. Those would be equivalent to one another, but let's ask a different question here. What's the relationship between this guy and that guy right there? Okay. Well, they're going to be equivalent as well. Okay, so that would be HA and HA. Okay, so let's take a look at that. How can we see if those are equivalent to one another? We could do a replacement test. Let's do the replacement test real quick so we can make sure we really see what's going on here, okay? So I'm going to draw it down here. So we have our H. Here's our 2 chlorines. So let's compare the relationship between those two to double check and triple check that they are in fact equivalent. So that's molecule A compared to this guy right here. Okay, so that's molecule A, that's molecule B. Can we take molecule B and directly superimpose it? Whoa, I did some too many X's. So that should be the H. There we go. Okay. So what's the relationship between HA and HB? Okay. So let's see here. How can we see that? Well, what if I take HB and flip it along its horizontal axis, and I'll draw it like this. CL. So let's just label this so you can see how I flipped it. I just took this whole molecule right here. So these chlorines right there are those chlorines right there. I just flipped it 180 across the horizontal axis. So now we have B prime. Now, when I flip that, that means my X is going to be right there. My hydrogen's going to be right there. So can I take that and superimpose it? No, I can't. And it's not a mirror image. But look at what I can do to it again. I'm now going to take B prime and flip it 180 degrees. Let's see here. Nope, nope. Let's look at it a different way. I was looking at it wrong. What if I took B and just totally rotated it this way? Okay. And now when I rotate it like that 180 degrees. Like that. Now what's the relationship there between this guy and that guy? You see how they're superimposable? Because they're superimposable now. Oh, I forgot a hydrogen. Okay. See how they're superimposable? You just plop them right on top of one another. That makes them homotopic. Okay, so now that we've double checked and triple checked that those are homotopic, we can come back here and say, okay, now what's the splitting pattern? So HA is attached to this carbon. What's the adjacent carbon? This guy. Why not this one? Because it's equivalent. It's the same one. We're only looking at the adjacent carbons that are not equivalent. And how many hydrogens are attached to that carbon in green? Only one. So HA is going to be split into a double then the other signal would be B, and that's equivalent. What's HB going to be split into? Well, it's attached to that carbon. What's the adjacent? Nope, that's not a carbon. HB is attached to that carbon. And what's the adjacent carbon? Right here. How many are there? 2 hydrogens. 2 plus 1 equals 3, which equals a triplet. Okay. So let's do this one right here. So we would have a chlorine like that. I'm going to wedge that chlorine, that like so. Hydrogen, hydrogen, hydrogen. Okay. So we have a plane of symmetry right there. So those are equivalent to one another. Those are equivalent to one another. And that methyl group is going to give a signal. So we would expect 3 signals for this molecule. And HA is going to be split into, it's attached to that carbon, adjacent singlet. There's no protons there, but that adjacent carbon there is protons. And there's 2 of them, so 2 plus 1 is 3, giving us a triplet. HB. HB is attached to that. And what's the adjacent? That's adjacent. There's no hydrogens. That's adjacent. There's 2 hydrogens. 2 plus 1 is 3, giving us a triplet. Then we have HC, which is attached. That's the carbon. What's the adjacent? Right there. There's 0 plus 1 equals 1, so that's a singlet. And then the last one right here. H's. Like so. Like that. Okay. So what you're going to find with this guy is all of them are equivalent. Okay. And so when we take a look at just one of them, that's the carbon. That's HA is attached to. What's the adjacent? Right there. Okay. Why not this one that I'm highlighting right now? Because it's the same carbon. They're equivalent. So those hydrogens are all homotopic, and HA is going to give us a singlet for all of those. Okay, I think that answers that. And if you need any help, just let me know.